Good morning, everyone. Thank you for being here with us today. I'm Abderraouf Khezaz from the University of Versailles and the ECE Paris School of Engineering, and today I will present to you some of our works. Here is a summary of how this presentation will go. First, we'll give you an introduction of the topic, so the problematic, what motivated our work and our objectives, then the tools and the methodology, how we try to answer the question. Then the model building, so this will go in detail into how the model that helped us solve our work was made, then the conclusion. So what is our work about? So those are the main topic of this study. It is basically an ADAS system, so a driving assistance system, where we will delve into the topic of ontology, knowledge bases, and UAV vehicle interactions. UAV are also known as drones. There will also be a part about a driving simulator that we developed for this work. So as we said, we work on vehicles and most specifically autonomous vehicles. Here you have the navigation cycle of an autonomous vehicle as shown in the work of Van Brummelen et al. As you can see, the navigation cycle is made of 4 different steps. We have the perception, the localization and the mapping, decision making, and the action. As you can see, the first node of this process is the perception one, meaning that the whole security and the whole the security and safety of different road users can be improved if we reinforce the first node of navigation, meaning the perception. So what do we mean by vehicular perception? It is basically the way a vehicle uses its different sensors in order to grasp the environment it is evolving in order to understand what's surrounding it. In order to do so, the vehicle, as we just said, it relies on multiple type of sensors. So here you have some of the most common sensors that can be found on an autonomous vehicle. As a matter of fact, those are the principal ones you can find on an autonomous vehicle today. So we have the LiDAR, which uses laser in order to map the surrounding and can also be used in some cases in order to calculate the distance between a vehicle and what's surrounding it. The radar, by using electromagnetic waves, can also be used to determine the distance between the vehicle, the ego vehicle, and another obstacle. The ultrasound sensors do the same, except they're using ultrasonic waves, so physical waves. We also have different type of cameras. So the classical monoscopic camera, it captures a continuous set of images and it processes them with image processing algorithm in order to classify the elements surrounding the vehicle and identify them. Stereoscopic camera is the same, except it is by using 2 or more cameras. And in addition to the classical roles of a monoscopic camera, it also adds a layer of depth. It can consider the depth of an object. And the thermal camera uses infrared and thermal emissions in order to perceive the surroundings. It is not as good as the other type of cameras when it comes to classification, but it works in harsher conditions. Now here you have the same sensors with their environmental known weaknesses. So most of the sensors are weak to either the weather or the brightness situation. As you can see here, most of the sensors are weak to some harsh climatic conditions, mostly due to the way the climate reflects the laser light, or simply because of the image obstruction. So considering the previous fact, we can wonder the following question, which is how can we improve an autonomous vehicle perception in a bad weather environment? The solution proposed in this work, and which is supported by the state-of-the-art we made, is the use of UAV in order to enhance the perception of a vehicle. The UAV has multiple advantages, mainly its small size, its ability to move in a tri-dimensional access, and also its ability to be stationed into some places that could be inaccessible to other vehicles. There are multiple ways to use UAV in complement to vehicles. Here are some of them, as said in the work of Menouar et al. We could either use them as a network node, meaning it would be like movable antennas, and they would help to increase the coverage of a small area, the communication coverage. They could also be used as a surveillance tool by for example, by the police. We could use them in order to watch a specific area and look for infractions. And this is the case that interests us, is using them as roadside units, meaning they would be stationed in a place where there is some hazard happening, and they could gather some more data and transmit them to the incoming vehicles. The use case proposed in this work is quite a basic one. We would have a vehicle advance in a foggy area where it has some limited visibility, and there will be a UAV stationed in the same place, which will gather some data about obstacles and transmit them into the vehicle. We would basically have two sources of information: the vehicle sensor and the UAV sensor. So we would need some way to fuse those two different data. Those data from different sources. In order to do so, we propose the use of a knowledge base, so ontologies, basically in our case, which are a formal way of describing a concept. It allows the presentation of an environment, a specific context, so we could basically store the different actors of some event, as well as the relationships between them or the different properties. Knowledge base played two roles, because thanks to some logical rules and to something called a reasoner, we could apply a layer of intelligence into this data and have some inferred results from what's in them. So it looks like a good way for us to fuse the data from different sources, which is what we're looking to do. The ontology developed in this work was populated with multiple classes. So we have classes for vehicles, we have classes for UAV, for car, we have a lot of sensors, and we have some relationship between them. We know that a car has multiple sensors. Sensor have weakness to either light, to either brightness or weather. So we have those different elements in our knowledge base, and we also have some logical rules. Here you have a basic logical rule. Basically, we have a car with fog sensors, and the fog sensor is calculating the value it's gathering, and if we detect that the value is over a certain threshold, then we can infer that there is fog in the area where we are, meaning that thanks to the element of the thanks to the element stored in the knowledge base and the data gathered by the vehicle, we know that we are in a specific situation. In order to test our concept, we developed a simulator in the Unity software. This is how the test worked. We had a human agent controlling a car, and the data virtually generated by the simulator were stored in the ontology, in the knowledge base, and were inferred thanks to the logical rules and to the reasoner. And the result of this inference and this intelligence was sent back to the simulator, and if there was some necessary information available to the human user, they were displayed into the screen. Here is the interaction between our different elements, technical elements. The Unity data are the Unity driving data, so the speed of the vehicle, the the data returned from the sensors are stored as JSON format, and they were sent to the Protege ontology thanks to a Python tool, the OWL ready Python tool. And the Protege, the ontology, if detecting that the UAV needed to activate its sensors, would advise the Unity simulator to do so. This was tested in 3 different use cases. So this is the basic and classical use case with no fog and no UAV needed. So in the simulator, the driver could see that there is a vehicle in front of it. So and the sensors of the vehicle could display the distance between the ego vehicle and the obstacle in front of it without the need of anything. In the second case, there was a lot of fog in the area, and the human driver could not see that there was an obstacle in front of it. Neither could the virtual sensors of the vehicle. So only when it was at a very close distance would the obstacle vehicle be displayed, meaning that most of the test subjects here crashed into the vehicle. And in the third case, this is the model we wanted to apply, we wanted to show. We have a UAV stationed in front of the vehicle, so on top of it. And there was still the obstacle in the fog, so could not be seen by the driver. And thanks to the different element of the model, meaning the UAV, the knowledge base, logging data, and requesting the help of the UAV, the UAV would gather some data from its sensors and send to the ego vehicle the location of the obstacle vehicle, telling it telling the driver where the obstacle is. And this information is displayed to the driver, who could then take the necessary action. We will now conclude this presentation with an overview of what we talked about here. So we presented an ADAS dedicated ontology, so an ontology which gathers data from a driving vehicle, store them, and process them. We use this concept in order to optimize the way a vehicle perceives its environment in bad weather. In order to do so, we also have a collaboration, an interaction between a UAV and vehicle. So the UAV support the vehicle ability to perceive its surrounding thanks to its own sensors and its advantageous position. And this concept was validated thanks to a simulator that we made specifically for the case with realistic physics engine and realistic virtual data. This work represents the first step in a bigger study. We still have some more objectives for this concept. Mainly, we would like to consider other type of environments, so an environment with brightness variation, with physical obstacles, with some unexpected hazards. We would also like to work deeper into the communication protocols, the way the vehicle and the UAV would communicate between them, using some secured type of communication. And we would also like to improve the set of rules that we have in order to support our previous points. We would like to thank you for your attention, and we are here if you have any question. Thank you.